Hello friends, today's question: a very long solenoid of radius r is carrying a current IT given as kt e raised to power minus alpha t, where k is greater than 0 as a function of time, which is also greater than equal to 0. Counterwise, counterclockwise current is taken as positive. A circular conducting coil of radius 2r is placed in the equatorial plane of the solenoid and concentric with the solenoid. The current induced in the outer coil is correctly depicted as a function of time, and we have to find out which of the graph is going to actually show about the current reduced in the circular conducting coil, which is placed equatorial plane of the solenoid, and it is also concentric with the solenoid. So let us start with the basic equation which gives us the magnetic field inside a solenoid. So we can say from here that magnetic field inside a solenoid and the formula for that is our B inside a solenoid on a point along its axis. That is our B, which will be equal to, let us write it as a time dependent function. So we have B of t is equal to mu naught n and I of t, where mu naught is the permeability of the free space. You can say mu naught is our permeability of free space n is the number of turns per unit length. N is our number of turns per unit length. Number of turns per unit length. And current we know I of t is the current as a function of time. I of t is our current as a function of time. As a function of time. And this current is given in the question itself, which is equal to kt e raised to power minus alpha t. So therefore, we can write that the magnetic field inside the coil, so from here we can say that our B of t will be equal to mu naught n kt e raised to power minus alpha t. Now let us consider that the outer coil is placed concentric with the solenoid. So magnetic flux through the outer coil. Magnetic flux through the outer coil. And we are given that the outer coil has a radius of 2r and it is placed in the equatorial plane of the solenoid, which is concentric to the solenoid. So we can write that the magnetic flux let us suppose that is represented as phi of bt through the outer coil. Through the coil, and this can be written as through the coil. So we can write that phi of bt will be equal to magnetic field multiplied by the area of the coil, which is our A, where A is the area of the coil. And we already know its radius. Radius is given as 2r. So its area becomes pi r square, which will be coming as 4 pi r square. Therefore, the magnetic flux phi of bt, so we can write therefore phi of bt will be equal to B. B we already found out is given by mu naught n k t e raised to power minus alpha t multiplied by the area, which is about 4 pi r square. So therefore we can write that the flux associated with the outer coil will be coming as 4 pi mu naught n k r square t e raised power minus alpha t. So this is the flux that is associated with the outer coil. Now let us find out the induced EMF in the outer coil because of this flux. So induced EMF in the outer coil. Induced EMF in the outer coil. And if induced EMF is the derivative of, or we can say negative derivative of the magnetic flux. So induced EMF is equal to negative derivative of our induced flux. So now we are going to derivate the induced flux. So we can say that our derivative of flux with respect to time t, this will be coming as 4 pi mu naught n k r square, and this will be equal to e raised power minus alpha t minus, and this will be coming as alpha t e raised power minus alpha t. So therefore the induced EMF it can be written as minus 4 pi mu naught n k r square e raised power minus alpha t minus alpha t e raised power minus alpha t. And because of this induced EMF, we can find out our induced current. Finally, we are going to find out the induced current in the outer coil. Induced current in the outer coil. So let us write it as I induced with respect to time t will be equal to EMF divided by the coil resistance, that is R coil. Okay. And R coil is, we are going to keep R coil as R coil because it is not mentioned in the question what is its value and what is its range. So we are only interested in the graphical representation. Therefore, we can write that our current induced IN with respect to time t will be equal to minus 4 pi mu naught n k r square and e raised power minus alpha t minus alpha t minus of alpha t and divided by resistance of the coil, that is our R coil. And this is the value of induced current. So from the graphical representation, we are going to find out what will be the value of induced current, particularly at time t is equal to 0. So let us find out the induced current at t is equal to 0. So we say at t is equal to 0, we can write that our induced current at t is equal to 0, if we substitute value of 0 in the given equation, this will be coming as minus 4 pi mu naught n k r square, and this becomes e raised power 0 minus alpha 0, and this becomes e raised power 0 and divided by R coil. So we get this as I induced at t is equal to 0 will be equal to minus 4 pi mu naught n k r square divided by R coil. So it means its value will be negative basically. So we can say it is going to start with a negative value. So in the graph, if we see that only one graph, that is option D, is having a negative value at the time t is equal to 0. First graph is having a positive value at t is equal to 0. Second graph is also having a 0 value at t is equal to 0. C graph is also having a value of 0 at t is equal to 0. So only graph which is giving the magnitude of induced current I at t is equal to 0 is negative, is option number D. So we can say that option D is the correct value, correct option rather. So we can say from here our option D, option D is correct. And from the expression, this expression rather, we can also get a rough approximate idea that the graph will be following, because the shape of the graph other than the initial point is almost same in every option. Okay. So from, if we see here also, here and in C as well as in D. The option basic shape is same. And if you see the value of the expression, not to the value but the induced value expression, here we see it is e raised power minus alpha t minus alpha t e raised power minus alpha t. So at what point it is going to increase, then it will be once again going to start to decrease. So we can get an approximate idea how the graph will be shaping up. But the most important point is finding out the value of the induced EMF at t is equal to 0. So this gives us a, we can say the option number D is the correct one. So this